Hello everyone once again. So in the last videos I basically just introduced the formal definition for a limit, the epsilon delta definition, and I gave a basic overview with one simple example for how to conduct a proof of a limit. So I just want to practice some more and we will continue with linear equations for this video. So for example, let's do the limit as x approaches 5 of 2x plus 3 is equal to, well, we kind of know that it's equal to 13 by just plugging in 5 for x. We know this, well, for now we just know this more intuitively, but we want to actually conduct a proof. So we will conduct epsilon delta proof. So first let's just state the definition of this specific limit over here. So it's for all epsilon greater than 0, there exists a delta greater than 0 such that this implication holds. So what is this implication? It's that the distance between x and 5 is less than delta but greater than 0, implies that the distance between 2x plus 3 and 13 is less than epsilon. So we want to prove this in order to show that the limit exists. So first, let's start with our givens. So we are given that epsilon is greater than 0, delta exists, there is some delta that works. For now we don't know this delta, but we will figure it out in this proof. And that the hypothesis is true. So the hypothesis is that the distance between x and 5 is less than delta and greater than 0. And basically you want to show that from these given assumptions, this this consequence logically follows. So remember, we start with the first part of our consequence, which is that, oops, 2x plus 3 minus 13 in absolute value. So we're going to start with this, and then we're going to show that it must be less than epsilon using our assumptions. So first let's conduct some algebraic manipulation. So this is 2x minus 10, which is equal to 2 times absolute value x minus 5. And then we see here absolute value x minus 5 is less than delta, meaning that 2 times that is less than 2 delta. So then this is less than, we see this less than sign, 2 delta. And then remember, we want this beginning piece to be less than epsilon. So we have this beginning piece, we have this less than, and then we want to do something in order to get epsilon at the end. So what delta should we use in order to make 2 times whatever value it is equal to epsilon, where obviously we should make delta equal epsilon over 2, so that the 2's can cancel out and we get epsilon. So then here, for this proof to work, we actually use delta equal to epsilon over 2. So here we go. The proof is done, and we showed that using our assumptions, we got that 2x plus 3 minus 13 absolute value is less than epsilon. And this proves that the limit is indeed 13. So now we can do another example. So let me do another trivial example. So limit as x approaches 1 of maybe 1/2 x plus 3 halves, and what would this be equal to? This would be equal to 2. So again, I guess we can state our definition for this specific case if we want to, but it's a little long, and by now it should be relatively obvious like what to plug in where. So let's just state our given. So epsilon greater than 0, delta, we will figure this out. and this hypothesis, x minus 1, the distance between x and 1 is less than delta and greater than 0. Okay, so now again we start with the consequence, and then we show that using our assumptions we achieve a desired result. So it's 1 half x plus 3 over 2 minus 2. So let's first do some algebraic manipulations. So here we can do we can combine 2 and or negative 2 and 3 over 2. That'd be 1 half x minus 1 half, and then we can take out a half, so x minus 1. We see x minus 1 here, so then we can do a replacement, so 1 half delta. And then here's another this is another cool thing. So we could directly go to the step where we find the delta such that where we find a correct value for delta such that 1 half times that is equal to epsilon. So we could do delta equals 2 epsilon. But in order to really like simplify everything, another thing we can do, this is the cool thing about kind of inequalities. We know that what's bigger than 1 half delta? Well, 1 half delta is just taking delta and dividing it by 2. So then obviously if we just have delta, that's bigger than a half delta because these are positive numbers. So this holds because 1 half delta is always smaller than delta for positive numbers, right? So then we can just do a simple, like in order to convert delta, in order to get epsilon from delta, we just say that delta is equal to epsilon, right? So then you could have done like 2 epsilon, epsilon, really anything smaller than 2 epsilon would suffice. And this goes back to just having the corresponding f of x values derived within the delta window being within the epsilon boundary. It doesn't need to be, it can be like comfortably within. It doesn't need to kind of snug up against the, the extremities of the epsilon window. Okay, and now let's do a more complex example. So let's say that instead of keep repeating the same thing over and over, where for example we do like 2x plus 1, 3x plus 1, 3.5x plus 8, let's just prove that the linear equations in general, so mx plus b, that these are continuous. So this basically means that essentially like plugging in your value for the function, so instead of x you plug in a, that this works, so that we can just use this method in a justified manner for whatever linear equation we come across. So one caveat is that m is cannot equal 0. We're not going to have kind of uh, like horizontal equations. We're going to do other types of linear equations because m equaling 0, it does mess with the proof. So we can just do 2 separate cases where m does not equal 0 and m equals 0. But first I'll focus on this case. So maybe here I'll actually write out the definition of the limit. So delta greater than, so for all epsilon greater than 0, there exists a delta greater than 0 such that this implication holds that x minus a, I mean x is, the distance between x and a is less than delta and greater than 0 implies that mx plus b minus m a plus b, this is what we're saying that the limit is less than epsilon. So this is what we want to show from our givens. Okay, so let's actually start with our just explicitly saying our givens. So epsilon greater than 0, delta we know is going to equal some value, which we'll discover in a proof, and the distance between x and a is between 0 and delta. Okay, so sorry about this constant movement. We have mx plus b minus ma plus b in absolute value, and then remember we just do some algebraic manipulations to use our givens and then get our desired result. So this is equal to, well, negative b, so plus b and negative b, that's just going to cancel out, and then we're just going to end up with mx minus ma, and then this is going to result in m in absolute value, because we don't know if it's negative or positive, but obviously it has to be, so we don't know if m is negative or positive, but the actual result needs to be positive, so we put in absolute value times x minus a in absolute value. So you know that x minus a is less than delta, so this is less than absolute value m delta. And then what do we set this to in order to get the final epsilon we desire? We set delta equal to, so what do we set delta to? We set it equal to epsilon over absolute value m. And remember, we are able to do this because absolute value, I mean, m is not like, m is not equivalent to kind of like x. Like x is the variable that changes, the thing that is getting closer and closer to a, whereas m is just the slope. Remember, it's going to be a context. I mean, it's going to be a constant in whatever limits we're trying to solve. So this is why we can actually use it within our delta value. So epsilon over m. So our delta is equal to epsilon over absolute value m. And then this results in our correct consequence. So this is really our first case because as we said above, m is not equal to 0. This is our first case. But then if m does equal 0, then mx plus b will just equal b, because 0 times x is just 0, and 0 plus b is b. So this is basically proving that the limit of a constant is equal to that very constant. It seems obvious to us, but a formal proof is needed in order to completely justify this. So it is a little deceptively simple. So let me just write out our givens. Epsilon greater than 0, the delta is going to equal something, and then the distance between x and a is less than delta and greater than 0. So the function is b, and we propose that the limit is equal to b. And then this is equal to 0, right? And then what we know is 0. So so we have this 0 is less than blah 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 is less than delta. So 0 is less than delta. But what we know also, we know that epsilon is greater than 0. So 0 is less than epsilon. So then we can just say that from our given that this is less than epsilon, and then basically we're saying that whatever delta value we use, it doesn't matter. It's always going to work out. So this is a special case where we actually don't need to figure out the delta value. It can just be any real number, just any real number, or sorry, any positive real number, because obviously it needs to be greater than 0. So then this is kind of deceptively simple, and I'll show you why the delta value doesn't matter. So let's say this is L, and then here is our B, which is also equal to the limit. And then let's say that this is our epsilon window. And then look here. If we have the delta window above here, we can see that whatever we choose, that whatever delta window we have, the the corresponding f of x values are just going to be the constant b. It doesn't matter what the delta window is in this case. The delta window can be here, and it's always going to be the same kind of resulting value. It's never going, because, and this is a special case because the f of x doesn't depend on the x. It doesn't change as x increases or decreases. So this is why here the delta doesn't matter. It's irrelevant in this case. But this is just, again, this is a very special case. Delta can be really anything. It doesn't need to even be considered. So you can really set it to maybe like any real number. You can just set it to like pi, 3, 100,000. It doesn't matter in this case.
Okay, so we just showed that that f of x equaling mx plus b, that is a continuous, basically meaning that as x approaches a of mx plus b, we are guaranteed that that is equal to ma plus b. That we can just substitute in that the value a that we're approaching into the function. So thank you for watching, and I hope to see you in the next video.